Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on Hooke's law. So far we've made the modelling assumption that all strings are inextensible. That really amounts to saying that what extension there is, what stretching capability there is so slight that we can ignore it and gain the benefits of a much simpler model. But when we can't make that kind of decision to ignore something, we need to have a model which takes account of that kind of the extensible behaviour. This leads us to talk about strings, for example the bungees, and springs, as in the picture there. And it leads to the concept of elasticity. Now, mathematicians make a distinction between strings and springs when they use the idea of elasticity. A string can be stretched and will give you resistance, but if you try pushing a string when it goes slack, it simply goes limp and you have nothing to show for your efforts. On the other hand, with a spring, it's different. So for a string, you've got tension only when the string is extended. But for a spring, you'll have both tension when it's stretched and compression when it's, believe it or not, compressed. So the idea of a string and a spring has a special meaning in mathematics which won't always correspond exactly to the use in the everyday world. So there we have our picture of how we're trying to model this. It's based on experimental evidence, which leads to what's called Hooke's law. The physicists tell us that providing you don't stretch too far, then the force that a spring exerts is proportional to the extension that it's suffering. So that means if you've got, say, 1 unit of extension giving you a force from the graph, if you go twice as far, see the x and the 2x marked on the picture, then you'll be twice as far up the f-axis. Now that's called proportional behaviour. You'll notice that the graph goes through the origin, where you've got an f is equal to a multiple times x. So our simple algebraic relationship is that f equals kx. In that form, the k is known as the spring constant, and it's a peculiarity of each spring. So a different spring will have a different spring constant. You might get two identical springs with the same one, but the point is that if you take a spring of the same material that's twice as long, you'll have a different spring constant. So K is often referred to as the spring constant or stiffness, and it's got units of newtons per metre. On the other hand, the more complex model, the one we shall use more usually, is the one which involves the modulus of elasticity lambda. So instead of K, you've got lambda over L. That corresponds to L is being the natural length of the string or spring, measured in meters of course. Lambda is the modulus of elasticity of the material. So if you get a spring that's twice as long but otherwise identical construction and materials, you'll get the same lambda. And lambda has dimensions of force, so its units are just newtons. Let's look at the first example using that more complicated model. We've got a light elastic string. Light, a word on that, it means that we don't have to take any amount for any mass into consideration for the spring or the string. That's like the old inextensibility assumption. You're saying it's really so slight that in comparison with everything else it can be ignored. So if we're finding the tension in the string, we'll need the model from Hooke's law, which is that T is lambda x over L. Now there are one or two things to be careful of here. It's pretty obvious that L is equal to 1.5 because that's the natural length, but be careful that the x is always the extension, so it isn't the 2, which you might possibly think. It's actually the 0.5, which is the difference between the 2 and the 1.5. So it's always the extension that we're interested in. So there we are. You see, we've got that the lambda is 50 from the question, and the L and the X as I've just specified, and there's our model. So the only thing we don't know is T, and that formula will allow us to work it out. So there we are. These things are really quite simple. Notice my usual drill of giving the calculator answer, or at least until I started to get lazy when I put in dots, and finally a rounded answer. So the answer to the question in context with the units is that the tension is 16.7 newtons. Now look at an object of mass, this time 0.5 kilograms. So again we're going to have the same situation we had before. We're going to have a weight which gives us rise to a 0.5 g, and we're going to have an equal and opposite tension because it's in equilibrium, so that will be 0.5 g, that's our T. We've got our natural length showing, so this is 0.15. Notice my usual convention of converting it to the MKS units, and then the units will be consistent. And this time the equilibrium height is, or depth is 18 centimeters, so the extension will be 0.03. Right, with that information we can get started. We've got the model, its T is 0.5 g, that's the equilibrium situation that comes from the picture here. And we've got T as lambda x over L, where we can put in the values for x, that's 0.03, and for L, which is 0.15, and we're trying to find lambda. So therefore we can put in our values having made lambda the subject. There's our statement of the values read from the equation. There's the equation with lambda the subject. We put in the numbers and we get an answer in context of 24.5 newtons for the modulus. Let's look at yet another similar situation, this time with the compression of a spring. So you can see that the 20 centimeters has already been converted into 0.2, that's the natural length. And the x is the extension, the difference between where it was and where it is now. The modulus of elasticity is 300 newtons, and we're going to use the usual model, so T is equal to lambda x over L, and into that we're trying to find x, and this time we're told that L is 0.2, x we're trying to find, and lambda is equal to 300. So that will enable us to do our calculations. Again, I've put in a force diagram. We're going to take the tension is the same as the weight, so from that equilibrium diagram T is going to be 4 g. So there's my calculations. A pity that one's on top of the other, but it's the same thing. So that will allow us to work out the model's implications. We'll end up having made x the subject, which is what we're trying to find. You see we've eliminated the t from these two so that we can say that 4g is lambda x over L. We've made x the subject by multiplying by both sides by L over lambda, and then we can put the numbers in. So we end up with a figure of 0.0261. Now here I don't go straight into saying that number is the answer. I think back to the question where the natural length was given as 20 centimeters, so we should, to be consistent, express this in 20 centimeters while we know that it's in meters, so that will be 2.61 in context, 2.61 centimeters. Right, now for a much more interesting problem which involves a bit of geometry. This is rather like a washing line with something hanging in the middle of it, except that a washing line would be rather longer. We've got a weight of 20 newtons hanging from a washing line, so we know we're going to have a force diagram something like this, 20 downwards, and you're going to have two tension forces corresponding to those strings up to A and B, so it'll be the same tension since it's symmetrical. Now look at the diagram. In order to get further we need to realize we can do some geometrical analysis. Imagine a vertical line there. That's going to be 0.5 meters long, and that splits the isosceles triangle into two parts. So you'll have an isosceles triangle something like this, where this is 1.2, the half of the 2.4, this is 0.5. You've got a right angle. Well, we've got a 5, 12, 13 triangle, haven't we? So that's 1.3. Now if we know that the natural length of that string, let's put that L is equal to 1.0, we can see that the extension for it is 0.3, because it's 1.3 in the situation. Now that allows us to do our analysis, so let's follow that through. First of all, we've got our diagrams. Now the additional feature I've shown here, before we look at the resolution, is that we need an angle alpha to resolve. There it is. Now that angle corresponds to the angle in the triangle, so we can use the triangle again, not just for the distances, but for the trigonometry. So if we resolve vertically, then what we'll get is that the component of t obtained by saying t cos alpha, two of them, will balance the 20 downwards. So from that we can see that t is 20 over 2 cos alpha and put the numbers in. The cos alpha comes from the triangle as 0.5 over 1.3. So that's arithmetic's fairly easy. We get 26. So that tells us that the tension in this force diagram is in each case 26 newtons. So now, armed with that information, we know that t is 26, we've just worked it out. The model says that t is lambda x over L. Now going back from the question, we need to find the values. L is 0.3 and x is L is 1, isn't it? That's a mistake. 1.0 and x is 0.3. If you substitute those numbers into that equation together with the t is 26, you'll get your value for lambda. So let's do that. 26 over 0.3, because the L is just 1, and we end up with 86.7. So that gives us a final answer of 86.7 newtons for the modulus. An interesting problem which requires a bit more than naive analysis. If we look back at how we did it, you can see that the first thing is that you have to think about the geometry and you have to think about the force diagram, and the two are quite separate at that stage. Okay then, so that brings us to the end of this particular presentation. The next one will be on elastic potential energy.